Just an overview of the talk. I'll first try to give a brief introduction to the CI/CoE pilot project along with the goals, then describe the data lifecycle abstraction that we came up with, and present it with an example case study with the IceCube large facility. Then I'll move on to presenting a DLC taxonomy across 4 large facilities, where we use the same DLC abstraction to describe some of the elements for 4 facilities, and then present a cross-cutting issue that cuts across all stages of the data life cycle, disaster recovery, and present a disaster recovery planning case study with IceCube. And then most importantly, this call is one of the goals of this call is to get feedback from the participants of the call to find out whether our abstractions and models of data lifecycle fits with other facilities. If we're missing anything, if we're missing any services offered at a particular stage of a data lifecycle, or anything that you think can improve on what we have as our current work. So the genesis of the project was in September 2017. The National Science Foundation held a workshop on cyber infrastructure for large facilities. So one of the major findings of the workshop was that there is a need for interactions, collaborations, and sharing across large facilities in terms of CI-related expertise, right? There's also a lack of easily accessible information that different large facilities could leverage for their cyber infrastructure stacks. And there was also a lack of a focused entity that could facilitate that sharing between the facilities, right? So one of the workshop recommendations was to establish a center of excellence similar to what is called a trusted CI, which is one of the centers for cybersecurity issues. So the idea would be such a center could facilitate these interactions across large facilities and serve as a resource providing expertise for CI technologies and best practices, and to help the community to interact, collaborate, and share, right? So that was the motivation for this project. And so the Office of Advanced Cyber Infrastructure and the Biological Sciences Directorates at the National Science Foundation funded us on this CI/CoE pilot project with a goal to develop a model and a plan for a cyber infrastructure center of excellence, right? So we wanted to be a platform for knowledge sharing and community building. We wanted to be a key partner in both establishment of new large facilities as they come up, and also during enhancements or operations with our expertise on cyber infrastructure architectures, best practices, tools, and other things. We want to be grounded in reuse of solutions across large facilities. So if we see that something is working on one large facility and we think that might be useful in a similar context in another large facility, we want to have that cross-pollination going. So that is one of the goals. We wanted to be a forum for discussions about sustainability, workforce development, and training. And we wanted to do all that and in the context of a pilot study for such a center of excellence with close engagement with one of the large facilities called the NEON facility, and then further engagement with other large facilities as we move forward, right? So these are the primary goals of the CI/CoE pilot project. And so one of the focus areas of our pilot project is data lifecycle and disaster recovery for large facilities. And that's what we would be presenting today. And so this includes work from the CI/CoE pilot team members, including myself, Laura Christopherson, Eric Scott, Ilya Baldwin, and Paul Ruth from RENCI. And then we have substantial input and collaboration and engagement with NEON personnel led by Tom Gulbarson, and from IceCube large facility, Benedict Ryder. So most of the work that I'll be presenting is a product of joint collaboration between these teams and these team members. So the goals of our of this focus area was to understand and document the best practices and solutions for data lifecycle and disaster recovery plans for large facilities. So we wanted to develop a generalizable data lifecycle model for large facilities based on our engagements. We wanted to come up with a taxonomy of the CI services, architectures, and functionalities that support each of these data lifecycle stages, and then come up with effective process guides for disaster recovery planning in the context of these data lifecycle stages. Now, what do I mean by data lifecycle, right? In a broad brush, what we mean by data lifecycle in our context, in the context of large facilities, is a general model that can capture the various stages the data goes through in the different large facilities, right? So this slide shows at a very high level view of what these different stages are. So by no means this slide shows everything in a very comprehensive way. Nor does it show all the intricacies that might be there in a data life cycle for a large facility. Some stages might not be there for some facilities. There might be some other stages that we might be missing here, right? So in very broadly, for each large facility, everything starts with data capture, right? It could be some type of sensors, distributed sensors. It could be large instruments like telescopes. It could be digital optical modules like in IceCube. It could be grapes, which are these field instruments, field sensors, which collect different kind of environmental data. So everything starts at a data capture stage of a data lifecycle, right? And then the data goes through some initial data filtering or processing. Most of the time, this stage happens pretty close to the place where data is captured. There are some facilities where nothing happens at the data source or the data capture location, but then there are some facilities where substantial processing happens on site near the source of the data, right? And then generally the data is moved to a central data processing center. It could be a single data center. It could be multiple data centers where a bulk of the processing and massaging of the data happens. And then since this data is very important, they're carefully archived and stored, maybe at multiple locations. And a lot of care is taken that no data is lost. And then data is disseminated, accessed, and published and distributed to the stakeholders, to the public, to the scientists, and to whoever the large facility serves, right? So these are, in a broad brush, the different stages of a data life cycle. And then there are elements which are cross-cutting across the data life cycle, right? For example, data movement is a kind of service that cuts across all these stages. Disaster recovery is another element where each of these stages need to have some kind of disaster recovery mechanism. What happens if something fails, right? Identity management is another. So I'm not listing each and every cross-cutting element, but this is a general framework that we're going to use in this talk to when you talk about data life cycle, right? So one way I thought to present the data life cycle is through an example, and so I'm going to present a data life cycle case study with the IceCube large facility, and most of this material is courtesy Dr. Rydell from Wisconsin, and so for each facility, everything starts with what's the data that the large facility is collecting, right? That's the high value thing, and we need to understand the data life cycle. We need to understand what kinds of data are captured, massaged, produced, and distributed by the large facility. For example, for IceCube, The data represents the hits in the digital optical modules, the events and the alerts and the metadata and the secondary streams, right? And then there are four kinds of data in IceCube. The raw data is called PF raw. There is filter data is PF filled, and then the higher level data products, level 2 and level 3 data products, which are more processed data products by either the central data center or by scientists who have access to the data. They transform it to other levels of data, right? So you see that this is a very common in our survey. This is a very common way how data is viewed by large facilities. There's raw data, and then there are different levels of processed data, right? And different things happen at different stages in the data lifecycle. So data capture for IceCube, because IceCube is a large instrument embedded in ice in the South Pole. It consists of strings of digital optical modules, which collect the data, and then the data is detected by servers on the IceCube lab, which is called the iStop. They're detected, they're filtered, they're sent to the South Pole station. Then data and then the filtered data is sent via satellite to the North Pole, to Wisconsin, right? So you see that data capture in this case happens at a single location because it's one large instrument embedded in ice. It might be very different for other facilities like NEON or OI, where things are more distributed, right? They're different sources of data. So data capture is the first step. As I was saying, there's initial processing and filtering of the data right at the South Pole for IceCube. The data is received by the DOM hubs in the IceCube lab. There are about 100 machines for detector readouts, and then there is about 500 core filtering cluster, which runs the rapid filtering algorithms to actually detect the alerts, which can be used by other large facilities. So this is where multi-messenger astronomy comes in, right? So you want to detect things really fast, so you want to process things right at the source. And then once the filter data is sent via satellite to Wisconsin, there are large clusters in UW-Madison where data is then converted to a science-ready level, right? So, and there is a huge cluster there. Then there's additional downstream processing that happens using a mix of resources at different sites: DESI in Germany, Open Science Grid, IceCube Grid, Exceed machines, or even DOE resources like NORSC. We see there's an increased demand for GPU resources. Different distributed computing middleware is used, and they're also exploring cloud resources. So as I describe the different stages of their life cycle, you will see that I'm not only describing the functionality for each stage, but also the services offered and the cyber infrastructure stack that supports that data lifecycle stage, right? So So the next aspect is the data movement, which is also important to understand the flow of data from the source of the data to the consumers. And we wanted to get into as much detail for understanding for each large facility how that's done, right? So in IceCube, there are hits at the DOMs, they're sent to DOM hubs. Then there's a data acquisition system where the hits are output as events. That's where the raw data is actually obtained. It's sent to the processing and filtering system, and in the IceCube lab, that's where the filter data is created. Then it's sent to the South Pole station, which is close to the IceCube to the IceCube lab, but still in the South Pole. And that's where there's something called the JADE system, which takes in the raw data and puts it in a disk, which is flown to Wisconsin once a year. And it's also the filter data and the raw data are archived there. The JADE also transmits via satellite to UW, as I said. And then the more filter data is sent to Germany, and the raw data from Wisconsin is also backed up on tape at NARSC, right? So it does take care as to keeping multiple copies of data in multiple places, keeping protections in place that they're not going to lose any data, right? Also interesting to see is there is this high volume data that goes through this path, but then alerts which are very low volume data, but which are sent using a different network called the Gamma Ray Coordination Network operated by NASA or astronomical telegram, so that those can be disseminated as fast as possible as soon as they see something in the South Pole, right? So also have to notice that for IceCube, there's limited bandwidth, about 100 gigs a day from the South Pole to UW, so they cannot send all the raw data even if they wanted to Wisconsin. So there are some limitations and in terms of data movement from the South Pole, right? That's understandable. As I said, once a year, the raw data is transmitted to Wisconsin from the South Pole, and then they use grid FTP and other mechanisms to transfer data from Wisconsin to other facilities, say to NERSC or to Open Science Grid, to other places. So we wanted to tear down how data movement is working within the large facility for this DLC stage. This just is a schematic view of what I told. In the interest of time, I'm going to skip this slide. The next important step is the data archiving step. So data storage archiving is very important for all large facilities because it's very high value data, and none of the large facilities want to lose any data, right? So the archival system for IceCube, it exists in 3 locations. The South Pole JADE writes 2 copies to disk. Then the JADE North at UW warehouses the data to disk. And then there is a long-term archive for the level 1 data in Germany. And then the DOE NERSC facility archives the raw data also, right? So you see that raw data is at the source in the South Pole. It's also at UW. It's also at NERSC. And even the level 1 data is archived and stored at different places, which is very important. The next data lifecycle stage is the data access, publish, distribution, visualization, where the stakeholders for the large facilities get to access the data that's collected, right? So for IceCube, there are 2 important kinds of data. One is what was calling as alerts, right? So dissemination of alerts happens very differently from dissemination of other process data. So alerts happen at South Pole, and then, as I said, the immediate alert is sent out using GCN with an initial estimate and a small portion of the raw data, and then when a full level 1 data is available at UW, a refinement of the first alert is sent to the scientists. Whereas for the larger volume of data that to access the entire data sets, mainly the level 1 data set, for IceCube, you have to be a member of the IceCube collaboration. There's also something called an associate member, which means one can use the data for a particular purpose, but it's not required to fulfill the collaboration obligations. And then data is also available on public web pages for IceCube. They do have current planned enhancements for how to organize and distribute and manage and catalog the data. So they are in a process of doing that. They are exploring an XRT based solution, maybe something like Ceph or www. Another thing is data is released to both members and associates, and then when the data has been analyzed and those analyses are published, it becomes available for release to others. So in that sense, IceCube is a little bit different, a little bit more conservative in terms of when the data is available to the scientists. And this is just a logical architecture for IceCube. And this is just a schematic of both the data flow and the cyber infrastructure that supports the processing of the data at different points. This just helps us to get a 10,000 feet view on what the large facility data movement and processing looks like. So I've now moved to so now that we have an example of what a data lifecycle might look like for a large facility. I'll move on to describing a taxonomy of this across 4 large facilities. So this is based on our current engagement with large facilities. For Neon and IceCube, we had deeper engagement with the CI personnel at the facilities. For OI, most of the information was obtained from publicly available information and one-off conversation with Rutgers CI personnel. For LSST, all the information was obtained from whatever is available publicly. So the taxonomy will definitely need to be refined as we have deeper engagements with OI, LSST, LIGO, and other facilities. So this is just a caveat before I get into that. Whereas information for Neon and IceCube are pretty close to what they are, what the systems reflects pretty close to what the systems are. Whereas for OI and LSST, there might be some gaps and some improvements that we need to do. Nevertheless, so I'll go through the different data lifecycle stages and contrast between the 4 facilities that I talked about. Right? I already talked about IceCube. For Neon, as you see about the data, there are 3 kinds of data for Neon. There are observational samples, instrumented systems, which are these sensors. Then aerial observability platforms, which means where there are airplanes collecting data, and then that data is sent to the central data center. And in terms of the levels of data, there are 6 levels of data from L0 through L0, L0 prime through L0 to L4. So different levels of process data happens in the central data center, right? So here you see that data is much more distributed. It is collected by about in about 100 sites throughout the United States, and it comes from different routes, unlike in IceCube. Similarly, for OI, as I understand, data comes from different kinds of sensors. There are cable sensors, undersea video cameras. Then there are also uncable sensors, which could be things on buoys, things on the ships and on the oceans. So all the data from these sensors flow to the East Coast CI through multiple routes, right? Things at the Pacific Rim, they get collected on the West Coast and they're sent to the East Coast, whereas many of the uncabled data takes a different route, right? So even for both Neon and OI, things are very distributed. They're collected using different kinds of instruments. There are video cameras. There are many other sources of data in OI. For LSST, again, like IceCube, it's one single instrument at one location, right? So it's in Peru, and then there are 3 types of data and different kinds of different data releases happen at different times. And it's also related to they also have this prompt nightly processing processing of alerts similar to IceCube. There's just a schematic of the different data capture instruments for the 4 large facilities. In terms of processing and filtering, as we see that almost there is no initial filtering or processing happens for Neon. Most of the data is just collected. Very minimal processing happens at the grapes or the smart sensors. So most of the data is just sent raw to the central data center. That's where things are processed through the different levels of data. So for OI, as I understand, there's some minimal parsing that happens maybe closer to the data, or maybe when the data comes to the shore, and then most of the processing happens in the U-frame infrastructure in the data center, in the Rutgers data center. Already talked about Ice Cube. For LSST, there's some processing that happens in the base facility near the source of the data, and that's where the real-time alert generation happens. The initial metadata creation and detector crosstalk correction; those are the things that happen close to the source of data. Whereas the bulk of the processing happens at NCSA, and some of it happens in France. So you see that for IceCube and LSST, there's some initial processing filtering that happens close to the source, but whereas for Neon and OI, most of the processing happens in the central processing place. For data movement, there are different paths for data movement. I talked about IceCube. For Neon, the three different sources of data for observational samples, for instrumented systems data, and AOP data, they flow very differently into the data center. For instrumented sense, for the IS data, most of the data is sent by the GRAPE systems, which are these distributed sensors on the ground, using public internet. Whereas the data that's collected by the airplanes, the disks are actually flown into the Denver data center. That's where they're just plugged into machines in the Denver data center, and then they're processed from there. Observation sample data is collected differently. For OI, for cable data, there's a different mechanisms in place to get that data. For uncabled data, we go through different paths. For LSST, there are special networks that are in place to move the data from southern hemisphere to northern hemisphere. They have multiple redundant network links from the base facility to NCSA, so that if one link fails, the other link works. So you see that even in data movement, there are commonalities and differences between the large facilities. For archiving, we see that most of the large facilities really take good care of storing the data reliably and making sure that they don't lose data. For Neon, they keep the raw data in multiple appliances inside their Denver data center. They also have cloud backups of their data. For OI, they keep copies of data in distributed fashion. They have one entire copy on the West Coast in Portland. The main copy stays in Rutgers, and they do also have copies of the data when the data comes to the shore, as I understand. For IceCube, as I said, it has different archives for different levels of data, and for LSST, I think they have long-term copies in 3 locations at the base facility in Chile. Sorry, I told Peru before. Chile and NCSA and France. So. For distribution, again, for Neon, there is mostly the data portal, and they do have programmatic APIs from the data portal to get the data. There's also work done by participants in our group to enhance data visualization capabilities for Neon and how data could be usefully accessed by the scientists. For OI, there's the OI data portal. There are thread servers. There's an ERDDAP server. The largest data sets are available on using NetCDF, which is hosted on a NAS at Rutgers. So different kinds of data access mechanisms are in place for OI. There is synchronous access, there is asynchronous access. So for LSST, data can be accessed from different places. It could be accessed at the base. It could be accessed using what they call the science platform that's developed by LSST, and there's also APIs that LSST plans to bring in. So this is just a set of cartoons for the logical architectures. That was for IceCube. This is for Neon. As you see, there are multiple types of data goes into the data center through multiple routes. This shows a schematic of what the data storage and storage infrastructure is inside the data center in a very schematic way. It doesn't show everything, just the high level elements. This is how we understand the logical architecture for OI. The multiple routes that cable data go through, and the East Coast CI and the West Coast CI, and what is the infrastructure that's supported at each of the data centers. This is the logical architecture for LSST. As you see, it comes from the telescope, goes to the base facility, to NCSA, and then to France. So that covers most of the data lifecycle work that we have been doing. And now let's move on to maybe I'll take the feedback and questions after I finish in 10-15 minutes. I think I'm doing good on time, so that will give us about 15 minutes for questions. So let's move on to disaster recovery. So disaster recovery is one of the cross-cutting issues across the different stages of the data life cycle. And when I tried to compare disaster recovery strategies for different stages of a data life cycle for the different large facilities, we can see that there's variation in terms of the protections that are in place at different stages. What I see is for data archiving and storage, all the large facilities are doing a great job at keeping these different copies of data at different places and making sure that they're not losing data, right? Whereas for other stages of the data life cycle, it depends on the buffering capabilities of the sensors. It depends on whether how long they can back up. For processing and filtering, we wanted to find out whether there are failover computing sites, whether things happen only at a central place, or whether there are other secondary places where processing could fail over when one of the sites fail. For example, in OI, with the West Coast CI could be used for failover processing if the East Coast CI goes down, right? Neon is planning to put a second data center in Wyoming where they could do some form of secondary processing. For IceCube, processing happens at UW, but it also happens in a range of distributed resources. So they are more resilient to failures of single system when it comes to processing. Even for LSST, processing is distributed at both NCSA and in France, right? So there is some protections in place for filtering processing. For data movement, again, there are redundant links between the West Coast CI and the West Coast CI and the East Coast CI for OI, so that's a good thing, right? So for Neon, I'd guess if there is a second data center, you could have some replication for data movement there. For LSST, there's redundant connections from the base to NCSA, which is good. That protects against network failures from Summit base to NCSA. So for disaster recovery strategies, this is just an initial estimate, initial draft on what we see as what exists today across these 4 facilities. So, so one of the cross-cutting findings that we came to after this initial survey on the data life cycles and disaster recovery is, although there are some disaster recovery strategies exist across some stages of data life cycle, disaster recovery hasn't been taken into account to the fullest extent when designing the architecture when designing the CI architecture for the large facilities. So we thought that there is some need for careful consideration of requirement analysis and planning for disaster recovery as an effective process that can be followed both before a disaster and after a disaster. So as a part of our project, we have been developing an effective processes guide for planning for disaster recovery for large facilities. And we have a working template that large facilities can follow for disaster recovery, and it's based on federal guidance for developing what they call as an information system contingency plan, ISCP, and by doing a business impact assessment. And this is based on guidelines coming out of NIST. So what are the major steps in an information system contingency plan? So it goes through three high-level things, right? It goes through an overview section where there's a top-level view of the cyber infrastructure disaster recovery needs for a large facility. Then we conduct a business impact analysis, which goes to three sub-steps, right? So first, it finds out what's the mission and the data life cycle of that large facility, described in a little bit more detail than the overview, right? And once we understand what the different stages are, we can determine what's the impact for outage when an outage happens for a particular stage of a data life cycle, right? What are the outage impacts? Then for each stage of the data life cycle, what is the estimated downtimes that a large facility is willing to it's willing to give, right? So what's the maximum tolerable downtime? What's the time when the facility wants to return to operations, right? So this needs some thinking and requirement analysis beforehand when the architecture is designed or when the architecture is enhanced. The next step is to find out what are the cyber infrastructure resources that's needed to support the disaster recovery mechanisms, right? And then the third thing is, what are the recovery priorities for these system resources? Meaning, when things go down, what's a priority in with which things should be brought back up, right? So, so a business impact analysis goes through these three steps, and once you have the BIA done, you create these contingency strategies for like, what's your backup and recovery strategy? What are the methods? Do you use offsite storage? Do you have alternate sites? Is there a plan in place for equipment replacement? What are the cost considerations for that? So it makes the CI architecture personnel think about in a very systematic way about what are the strategies to take, how to plan for a disaster recovery. So we've created example and disaster recovery planning templates for IceCube and Neon, and engaged with them to validate them and refine the template. And in near future, we plan to engage with other large facilities to go through this exercise, right? So to give you a flavor on what we did for DR planning for IceCube, I just present some of the steps that I described in the last slide, right? So for the first step for doing this information system contingency plan is to find out what's the business mission and the data life cycle for the large facility. So this I don't need to explain in detail because the data life cycle kind of sets up the context for disaster recovery. So these are the difference to describe what the different stages of the data life cycle are and what they entail, right? And then for each stage of the data life cycle, we try to estimate the impact of outage for that step, right? And these impacts could be different types of impacts. It could be the impact to the mission of the large facility. It could be impact on the cost. It could be impact on the science return. It could be, and then we come up with an overall impact of overall impact level for that stage of a life cycle, right? And then the impacts could be like severe, moderate, and minimal. And then when we went through this exercise with IceCube, we realized that there are different kinds of impacts for different stages of the life cycle, right? For example, initially we had disseminate data as a single step in the data life cycle, but we understood that that the alerts were more important than access to level 2 and beyond processed products. So the mission impact for alerts failing is severe, whereas mission impact for distribution of high-level data is moderate, or the science return for the minimal. So things could be down longer for dissemination of high-level data products than for alerts, right? Same for processing of data. The processing for alerts are more severe impact than others. So this framework helps you to think through these steps. Once you know the outage impacts for the different stages of the life cycle, what you want to see is what are the estimated downtimes for this stage of the life cycle, and what's the maximum downtime that can be tolerable. That's the MTD, right? RTO is the recovery time objective, which means when a particular life cycle stage goes down, within how much time do you want to bring the systems back online, right? Which is different from MTD, where you can tolerate that much downtime without affecting significantly the mission of the large facility. So we came up with these numbers after discussions with the CI personnel for the large facilities, right? Which I think again helps one to prioritize and think through the steps and the resources needed for disaster recovery. And that gets to what are the resources that support the data life cycle stages. We need to elucidate that. And then when a disaster happens, what's the priorities? What's the priority for recovering different parts of the system, right? And that will be dictated by the RTO numbers, but it again it helps you think through the process. So this gives you a flavor on both the data life cycle and disaster recovery planning work that we have done. I just wanted to end with a few lessons learned slides in terms of like when we engage with these two large facilities, what are the things we can conclude or what are the lessons that we learned, right? So data lifecycle is just one way to learn, reason, and catalog the CI functionalities for each stage of data operations for large facilities. The DLC abstraction helps reasoning about what services are offered by each DLC stage. What are the CI architecture elements that support each DLC stage? The other thing we realize is there are both fundamental commonalities and differences across the large facilities for their life cycle. Not surprising, but again, the devil is always in the details for both the DLC and DR. Many a time, specific elements or types of data are prioritized for a large facility. Also, there's heterogeneity of data processing. The set of processes handling the data differs according to the type of the data. Heterogeneity of tools and CI stacks for the same operations across different stages of the lifecycle or across different facilities. We also thought that the DR planning template was a good way to start thinking about disaster recovery. It's a framework to document and prioritize the CI architecture and operations. That template can also be used by large facilities to quantitatively justify CI elements for construction or future enhancements. And finally, effective communication between the large facility CI professionals and our team was key to the thorough understanding. There was available documentations and reports. They're necessary, but they're not sufficient. Only after we really engaged with questions back and forth, with drafts of the planning template, that's when things start getting crystallized. So that concludes my talk, and I would really like to get some feedback from the participants in the call about what do you think about this approach, both for their life cycle and the disaster recovery templates. And thank you for listening.